Okay, in this video I will go through section 2.6 of chapter 2 of FS1, which is using the Python distribution to approximate the binomial distribution. Okay, so sometimes we have to approximate approximate the Python distribution binomial to Python distribution. So why we do that and how we can do. Okay, let's assume x follows the binomial distribution with number of trials of n and probability of success is p, and n is large and p is small. Then x can approximately become Python distribution with a rate of lambda, where lambda is equal to n times by p. Okay, so we say n is large and p is small, but there isn't a definite value for n and p to say n must be definitely this value or greater or less than this value and p must be this value. However, as far as n times p is less than or equal to 10, then we can approximate binomial to Python distribution. Okay, so this is how we approximate, but what's the point and why we do approximate binomial to Python is when n is quite large number, it becomes extremely difficult to calculate the probability using the binomial formula. Okay, so that is why we can convert it to Python to calculate it easily using the Python distribution. Okay, so let's look at the example 1 or example 10 from the textbook. Okay, the random variable x follows the binomial distribution with number of trials of 200 and probability of success is 0.03. Find probability of random variable x equal to 4. Okay, to find probability of random variable equal to 4, I have already written the question here just to save our time. Okay, so x follows the binomial distribution with number of trials of 200 and probability of success is 0.03. Probability of x equals to 4. Okay, let's apply this formula. I have already written the formula here as well. N choose x. What is n? N is 200. Number of trials is 200. Okay, choose x. We are looking for 4. Times by p to the power of x, where p is 0.03. Okay, to the power of x, which is 4, times by 1 minus 0.03 to the power of n minus 4, 200 minus 4, okay, which is 196. So, using the calculator, we would get 0.1338 up to 4 decimal places. Okay, so it's not easy, as you see, without using calculator. It won't be easy to calculate 1 minus 0.03 to the power of 196. However, in this case, it was possible. Okay, in some cases, it is really impossible to do that. So, part B, it says a Python variable y follows the Python distribution with rate of lambda is used to approximate x. Write down the value of lambda and justify the use of Python approximation in the context. Okay. So, under Python distribution, it would be y follows the Python distribution with lambda, where lambda is n times p. Okay, so n is 200 and p is 0.03, which is 6. So, therefore, lambda would be 6. Y follows the Python distribution with a rate of 6. Okay, so as n is large and p is small, then x can be approximated to Python. So the justification for that, n is large and p is small. Okay, so we can clearly see that n times p is less than or equal to 10. Therefore, Poisson distribution will be suitable approximation. Okay, so let's move on to part C, which is the last part. Find probability of y equals to 4 and comment on accuracy of the approximation. Okay, we already worked out probability of x equals to 4 using the binomial distribution. So let's try probability of y equals to 4, okay, using the approximation to see the differences. How much there is differences. Are they close to each other or not? If they are, then the Poisson approximation would be definitely suitable approximation. So probability of y equals to 4, as it's a Poisson distribution, it would be e to the power of minus lambda, which is minus 6, times y, lambda to the power of x, which is 6 to the power of 4, okay, over 4 factorial, which is 0.1339 to 4 decimal places. So we clearly see that this one is 0.1338 and this one is 0.1339. Okay, so therefore there is only extremely small differences between these two values. So the answer obtained from the Poisson approximation is very close to the value for the binomial distribution. So the approximation is accurate. To justify this, we write down the value obtained from the Poisson distribution is very close to the one from the binomial distribution. Therefore, the Poisson approximation is suitable. So that's the end of the lesson now, and you should be able to do exercise 2G from the textbook, which is page 36, 37, and 38. Page 36 to 38. Okay.